Welcome to the second lesson of distribution. So, in this lesson, we're first going to define the units that are utilized for energy. And then we're going to talk about the relationship among those energy units because if you recall from our first lesson, we spoke about different type of energies that we have, mainly being heat, electrical, as well as mechanical. So now we're going to be looking at their units that they utilize to measure that type of energy that they have. Then we're going to calculate the efficiency that you can be able to get out of a certain unit. And then we are going to talk about the classification of the power stations and the different type of power stations that we have. And we're going to end this lesson by just looking at the steam power station. Then the remainder of the other power stations we're going to be looking at in the next lesson. Otherwise, the lesson will be too long for us. So we need to remember that when we talk about energy, we're talking about something moving. And we call that basically the ability to do work. So that is what energy really is going to be. Now, the most important forms of energy that you're going to learn in this course is mechanical, electrical, and thermal energy. And these three energies, we see them as being interchangeable. In other words, you can move from one form of energy to another. And it is possible to then assign the same unit to them. So for mechanical energy, the unit is called the Newton meter. Or we can utilize Joule, which is on the SI system, that is your international system of units. So the work done on a body is 1 Newton meter or a joule, and if a force of 1 Newton moves it through a distance of 1 meter, and this can be simply written as mechanical energy in joules will then equal to a force in Newton multiplied by a distance that force is moving in meters. So in electrical energy, the unit of electrical energy that we utilize is called a watt second or a joule, and is defined as follows: that in 1 watt second or joule, you have got energy that gets transferred between 2 points if there is a potential difference between those 2 points of 1 volt. And then between them, you have got 1 ampere of current that will pass, and that will pass for only 1 second. So that is what we call the 1 watt second. So this means that your electrical energy in watt seconds simply becomes voltage in volts times your current in amperes times your time in seconds. Now remember, your voltage times your current is equal to your power, right? So therefore, your power multiplied by the time is what is going to give you the energy. So your joule or your watt second is a very small unit, and we don't usually refer to them in that manner in electrical engineering. We always, or most of the time, would refer to bigger units such as we would say a watt hour, or in most cases we would say a kilowatt hour. So for us to get to the watt hour and the kilowatt hour, this is what we need to do. So to get to the watt hour, it means that we've got 1 watt multiplied by 1 hour. Now we need to transfer the hour into seconds. So we know that an hour has got 60 minutes, and then if you want to get that further down into seconds, you times by another 60. So an hour would be equal to 3,600 seconds. So therefore, 1 watt multiplied by 3,600 seconds would give me 3,600 watt second. Then if I wanted to take that and move it into kilowatts, I simply would take that 3,600 watt second, divide by 1,000, and that would give me 3.6 megajoules. Okay, so 3.6 megajoules is therefore equal to 1 kilowatt hour of energy in electrical. Then the last one we look at is the heat energy. And for heat energy, we say that it is a form of energy which produces the sensation of warmth. So we always think about heat, and we think about fire, and we think about the heater. So we think about something that is warm. And the unit for this is in calorie. Not the calories for fat or the calories that you find in food, but we call it calorie. That would be your heat energy. So a calorie in this case is the amount of heat required to raise the temperature of 1 gram of water through 1 degree Celsius. So 1 calorie is equal to 1 gram of water multiplied by the 1 degree Celsius. And if we look at Wikipedia, you will see that you've got a small calorie or gram, usually denoted a calorie, is a small amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So your large calories, just like in electricity that we talked about kilowatts hour, so your large calorie or food calorie or is called here a kilocalorie, which is K cell. And it is the amount of heat needed to cause the same increase on 1 kilogram of water this time. So you simply divide what you had by 1,000 so that you can get it to be the kilogram. So whether we are looking at electrical, mechanical, or thermal energy, the common factor of the energy is that it can do some work. So therefore, mechanical, electrical, and thermal energies must have the same unit. That's why we always relate them to joules. And there exists a definite relationship among the units assigned to these energies, and these units are related to each other by some constant. So we can move from mechanical to electrical by just multiplying by a certain constant, and also move to thermal by doing the same. So for your electrical or mechanical, we say that we've got 1 kilowatt hour, which is equal to 1 kilowatt multiplied by 1 hour, which we've already explained that the 1 hour would become the 3,600 seconds, and we said that it gets us to 3.6 megajoules. So therefore, electrical energy can be expressed in joules instead of a kilowatt hour. So 1 kilowatt hour, we must remember, is equivalent to 3.6 megajoules. Then if we go to heat and mechanical, we've got 1 calorie, and that is represented by 4,187 joules. And then for your electrical and heat, you've got the 1 kilowatt hour, which is equal to 1,000 watts multiplied by 3,600 seconds, the 3.6 megajoules. And then if we take that and we divide by the 4.187, which is your heat and mechanical, you would get the 860 kilocalories. So 1 kilowatt hour, when we're looking between electrical and heat, it will be equivalent to 860 kilocalories. So just to summarize the slide, between electrical and mechanical energy, you will have your 1 kilowatt hour being equivalent to 3.6 megajoules. Then between your heat energy and mechanical energy, your 1 calorie, which is what is measured in heat, will be the same as 4.187 joules. So therefore, between your electrical, which was the first one that you had, and your heat, which is the second point that you have, you will take that 3.6 megajoules that we had on the first one, and you divide by the 4.187 we had on the second one, and that will give you the relationship of 1 kilowatt hour then being equal to 860 kilocalories. So now that we've looked at the different units, we're now quickly going to look at one example where we're calculating the efficiency. So here you've got a mechanical energy that is supplied to a DC generator at a rate of 4,200 joules per second, and the generator delivers 32.2 amps at 120 volts. So the first question they ask is, what is the percentage efficiency of your generator? And then after that, how much energy is lost per minute of operation? So let's first start looking at the first one, the percentage efficiency of the generator. Now, you've got an input power that is 4,200, and that, because it's joules per second, we can take it as 4,200 watts, because remember, your watts multiplied by your seconds would be the one that gives you energy. So if we say now the output power is then VI, which is the 120 multiplied by the 32.2 that you're given, it will give us the 8 the 3864 watts. Then for our efficiency, it simply becomes your output divided by your input power, and that would be the 3864 divided by the 4200, and in percentage, that is 92%. So the efficiency of this engine or this generator is simply 92%. Then we look now at the second question that asked how much energy is lost per minute of operation. So for us, we first must look at what is the power loss in the system. So your power loss will be your input power and we subtract your output power. So therefore, it's the 4200 minus the 3864, and that will give us the 336 watts. And then the energy there per minute, okay, means that you take the power and you multiply it by the minute, and the minute is in seconds. So we know that 1 minute is equivalent to 60 seconds. So therefore, you would have your energy loss per minute being 20160 joules, which you can obviously divide by 1,000 and say is 20.16 kilojoules. So with what we've looked at now, we're further going to define your calorific values, and that is known as the amount of heat produced by the complete combustion of a unit weight of fuel. So that's what the calorific value is. And then we say that this calorific value indicates the amount of heat that is available from your fuel. And the greater the calorific value of fuel, the larger its ability to produce heat. So therefore, in the case of a solid and liquid fuels, the calorific value is expressed in megajoules or ton or kilojoules per kg. So it's calorie per gram or kilocalorie per kg. So in gaseous fuels, it is generally stated as your megajoules per meter cubed, or it's your kilojoules per liter. And this slide, just simply for references, is showing us or giving us the calorific values for the different type of solid fuels that we have, the different type of liquid fuels that you would have, as well as the different type of gaseous fuels that you would have. So those are all their calorific values. Then we look at the various type of power stations that you will get, and the power stations are where our electricity is getting generated. So we first talked about the sources of energy, and then we went and talked about how those energies can be measured, and that they are called mechanical, electrical, and thermal or heat. So now we're looking at how we're generating power, and we're going to be looking at how those energies come into play into this generation, as well as how the sources of energy get utilized. So the first one is the steam power stations. Now, some people, depending where you are in the world, would call these the coal power generating stations. Okay, so they are the same thing. Coal power generating stations or steam power stations is one and the same thing. And these are the pictures that you have for them, where you can see you've got those big towers that we call the cooling towers, and then those small thin cigarette like figures are called the smoke stacks, and that's where all the bad gases would get emitted into the air, whereas your cooling towers get utilized to cool the water that is used in that system. And then the process is going to be explained further in the slides. Then just quickly looking at the other substations, although we're not going to go in detail with them at this lesson. So the first one is looking at the hydroelectric power station. And this is the one where you utilize water that is stored at a higher level, and then when it releases down to the lower level, that's how they generate the power. Then this is your diesel power stations, and we're lucky being in East London because we've got one that is called Podrex. So Podrex is also on this picture. It's the one at the bottom right hand picture. And when you look inside the power stations, that's what you would find the top pictures on both the left and the right. Then we have nuclear power stations. Again, in the country, we're lucky we've got one that's in Cape Town and it's called Koeberg. So those first two pictures at the top are Koeberg Power Station, which resides in Cape Town. And then you've got the bottom ones where I've taken some of the power stations, like the one on the left-hand side is a power station in France. And then the one on the right-hand side at the bottom, we took from a picture of the Guardian on the internet. Then we now look at the classification of these power stations. So as I've said, we have got, depending on the form of energy that we get converted into electrical energy, the generating stations are classified under the following: a steam power substation, or rather a coal-fired power station. You've got a hydroelectric power station, you've got a diesel power station, and a nuclear power station. And luckily, you've seen all the pictures now. So your thermal station is a generation station that converts heat energy. So the heat is coming from burning the coal and into electrical energy. And that station is known as a steam power station. So your coal-fired plants will produce electricity by burning the coal in something called a boiler. And once the coal in the boiler burns, we produce steam. So the steam that comes from the water that was boiling in the boiler, which was heated by the coal, would then be under a tremendous pressure, and it would flow, it gets captured and flows into what we call a turbine. And then the turbine will spin the generator, and that is what creates electricity. So the steam is then cooled off and it condenses back into water, which we then return back to the boiler, and the process will start all over again. So in the station, you had heat energy of the coal that was utilized to burn that coal and transferred into electrical energy, which is what we got out of the generator. So on this slide, we're looking at the process of how all of this works. So you've got coal at the top left-hand side, that is your supply coming in. It goes into something that is on the gray here called a crusher. And then from that crusher, which now takes these granules of coal and basically crushes them into something that almost is powdery, it gets then transferred into what we call the furnace. And basically, the furnace is where the coal is then heated. And above the furnace over there, you would have your boiler, and your boiler would be what your water is put into. And you can see from the bottom there that you've got water from the water treatment plant that is going up these pipes and going into your boiler, which is just above your furnace. So the furnace is heating up and the water is boiling. Once the water boils, it will produce some steam. So the steam is then taken from that and it goes into our turbine, which is that top picture there, all right? So the turbine, being that gray top picture on my right-hand side, will then be connected to your generator, which is what would be able to produce electricity for you. So what I want you to look at now is at the bottom of this picture. So while the coal was going up to your furnace, there was some ash that comes out. As you know, even if you have a braai or you make a fire, okay, there will be ash that will be coming out at the bottom. So that ash gets collected and goes out into our ash handling plant. Okay, in this case, there is a truck that is collecting the ash at the bottom there. But in most cases, in your power stations, you will not have a truck, but there will be a plant that ash gets taken to, so that they can be able to dispose of it correctly. Then also, if you're looking at the water side now, after your water has gone into the turbine, the steam would cool off. Remember, it was steam going to the turbine. It would cool off. Then once it cools off, it goes back down. So we recycle the water. It goes back down and condenses, and we call that our condenser. So once it gets to that condenser, it will then be processed into the water treatment plant again. So we send it back to the water treatment plant so that it can be cleaned and reprocessed, and it will go back into feeding again your boiler over there. So those are the plants that we have. We've got the coal and ash handling plant. We've got the steam generating plant, which is at the turbine as well as coming from your boiler. Then we've got the steam turbine itself. We've got the alternator, which is the generator. Then we've got the feed water that is coming from the water treatment plant and going into the boiler. Then after that, we've got the cooling arrangement, which is now that steam that was coming off from your turbine that condenses and goes back into the water treatment plant. So, how to best optimize the location of your power stations is to ensure that the following points should be considered when we're selecting its site. The first one is your supply of fuel. So remember, your fuel in this case was your coal. So we need to make sure that our power station in this case should be located near coal mines so that the transportation cost of the fuel is minimum. Now, at a power station that I worked at in Mpumalanga, which was Matla Power Station, we were right next to a coal mine called Matla Coal. And basically, there was no transportation costs or trucks that were utilized to bring the coal from the one to the other side. All that they did is that they had a plant that transported the coal via conveyor belts from the mine into the power station. And when it gets to the power station, it's put into stacks and then released into the power station as and when it is required. So you want to make sure that you are close to your coal mine. The second one is availability of water. Because you are going to use huge amounts of water for the condenser. Therefore, such a plant should be located at the bank of a river or at least near a water canal. So, although we're saying we don't really require transportation of the coal itself, you still need to be able to transport your material as well as your machinery. Even your personnel need to be transported into the facility because they don't live on the power station itself. They'll be probably living in a town nearby. So you need to make sure that you are close to roads or some form of transportation method. Then the cost of the type of land that he utilizes should be such that it's located at a place where the land is cheap and further extension is doable. In other words, you can start your power station small, but in 20 years' time, you want to expand, you should be able to have that expansion where your current station is without you now having to go and build somewhere else. So, that is what you require when you look at your type of land. Then we want it to be near as possible to your load centers. And what are your load centers? In order to reduce the transmission cost, that is now your electricity that was coming from the generator, you want your plant to be located near the center of the load. So as close as possible to where the load is. And I think that is why in South Africa, we've got our control center or the big transmission center sitting in Joburg, So all of these power stations from Mpumalanga and Limpopo and the one or two that's in Joburg would all get transporting their electricity to this one place. So that's why we want it to be closer to the school center. Then you have the distance from your populated area. So as much as we say there are people that works here, but you don't want your station to be very close to where your people are living, as there is going to be a huge amount of coal that is burnt and in the steam power station. So therefore you're going to have smoke and fumes that are going to pollute the surrounding area. You want to protect people from that. So now we look at the steam plant on your thermal and the overall efficiency that it has. And we say that the greater the temperature difference, the greater the amount of heat that you would lose. And this explains for the low efficiency of those plants. So we say for the thermal efficiency, remember we use thermal energy here, the ratio of heat equivalent of mechanical energy transmitted to the turbine shaft to the heat of the combustion of the coal is known as your thermal efficiency of your steam power station. So from that thermal energy, we have mechanical energy, which is now where your turbine gets into kick. And when the shaft of that turbine starts turning, going into then the generation of the electricity. So our thermal efficiency being equal to heat equivalent of the mechanical energy transmitted to the turbine shaft over the heat of the coal combustion. And we usually say that the thermal energy of a modern steam is about 30%. And the overall efficiency is equal to the heat equivalent of the electrical output divided by the heat of the combustion of the coal. So remember, there is two efficiencies here. There is the thermal efficiency, and that was heat equivalent of the mechanical energy that is transmitted to the turbine shaft, and we divide by that by the heat of the coal combustion. In the modern substations, we say this is 30% of your thermal energy. Then we've got the overall efficiency, and that is your heat equivalent of electrical output divided by the heat of the combustion of coal. And the overall efficiency of these steam power stations is also more relatively close to 30, is usually sitting at 29%.